All right. Sorry, I'm a few seconds late there. I do a discussion at the hour block just before this, and I'm recording these so that I can provide them on iLearn if you need them. And it turns out the 10-minute break between these two is like just short of enough time to like make the video file when I turn Zoom off. So I'll figure out something else that doesn't interfere like that in the future. So welcome to your first discussion of 2B. It's going to be pretty different doing it online. So I don't know how 2A was done, but I know what we're used to doing is we're used to giving you like worksheets, sort of having you just have at it and maybe popping in to see if you have any questions about the stuff. I don't see how that can like effectively be done in this format. I mean, obviously I could do it and just like be like, hey, you know, you have the worksheet, it's on iLearn, work on the problems, and then I go through them. I don't think that's an effective use of the time. So what I thought we would do is I will sort of slowly go through the problems. Slowly meaning like, I don't expect you to like have to actually chime in. Obviously, if you have a question, you know, just go ahead, unmute, ask a question. But I'm not gonna like sit here being like, you know, anybody know the answer, Bueller? I'm just sort of like give a brief pause as I'm going through the questions to give you a chance to just internally sort of like think of an answer for it and be proven either correct or incorrect when we get to the answer. It's obviously a format that can be abused, where you know, just sort of sign in, go off and do your own thing and do nothing, because the only grade that we give for this is attendance for discussion. That's it. Your discussion score is a 1-to-1 ratio of how often you attended. And I'm going to figure out a way to do that. Right now it's week 1. Whenever I teach a class, I always just give a gimme for week 1 anyway. Whether you're here or not, you're marked as here for week 1. I'll figure out something. I think you can like export the participant list or something. I could do that in the future. But right now, everybody's here for week 1, so no worries. I guess it's just important to know that this is beneficial for you. Like how discussion is helpful. Just it depends on how much you are mentally engaged in it. You know, if you just show up and just sit there waiting for it to end, you're not going to get much out of it. And in fact, it's probably not worth your time if that's how you're going to treat it. You can just, if you do better studying on your own, just sign in, have your name on the participant list, and study in your own way. Yeah, I don't want you to waste time on something that's not helpful for you. But in general, across the board, statistics will say that discussion is helpful. Just depends on how much you engage. And I think that's why they always force the group work, because it kind of forces you to engage in it. Not everybody does well in groups, I get that. So Zoom is a chance for us to do it this way, where I can just sort of slowly go through the stuff and have you sort of like think about what's going on and whatnot. As far as questions for like what goes on in lecture, I can go over those in office hours. I have specific worksheets that they want me to go through and like specific problems that they want me to go through for discussion. And in my experience, having taught this twice before and then having just done a Zoom discussion an hour ago, an hour is barely enough time to get through the stuff that they want me to get through. So let me get my email. Let me get all the administrative stuff out of the way. It's week 1. This is what we got to do. So my name's Brian. Nice to meet you. My email and my terrible handwriting are going to be up on the shared screen right now. So this is the format that I do, and I'm sorry, this is F-R-A-N. That is not an M. It's an N. BFRAN 005 at UCR.edu. Office hours. I don't have the exact hours down yet. I'll have them tonight or tomorrow. But I do this 2-hour block Monday and Wednesday from noon to 1 and 1 to 2. And I thought picking the 11 to noon block on either Monday or Wednesday, and then the 2 to 3 block on the other day for my 2 office hours. So I have like an hour before that block, an hour after. That gives a morning hour office hour and an afternoon office hour. I'll figure them out and I'll put them up for everybody to know. If office hours end up falling in such a way that they're just not beneficial for you, you just can't make it, you can always email me. I'm willing to answer questions over email, and in some cases, I'm willing to meet outside of the office hours if you have a question. If it becomes a weekly thing, I might just change my office hours to that time then, because it's like I'm just doing another office hour that time. It's not a problem. It's just I'll just let you know that might just make me change my office hours. So I think that's everything administrative-wise. My email, my office hours, my email policy, like I said, go ahead and email me questions. That's fine. And yeah, like I said, discussion, we're sort of pressed for time all the time, and I have these specific things that I'm supposed to go over with you. So any questions related to like lecture or homework, that would be office hours and email stuff. All right, so like I said, I don't think the group work thing is going to be effective on Zoom. I could do breakout rooms or something like that, and that's just too much work. That takes up too much time, and we're already pressed for time. I'm just going to slowly go through the problems, and we'll start with number 1. Oh, yeah, this came up in the last one. These discussion questions that I'm going over, they are worksheets that become available on the main iLearn page for 2B. So the one that's handled by Professor Mulligan, not the separate discussion iLearn page that I'm in control of. He has them on a timer, and I think he makes them appear at like 5 p.m. the day before or something like that. I forget what the timer is, but basically I guess a good practice would be like the night before discussion, pop on iLearn, like I think Sunday night or Monday night. You pop on iLearn and the discussion sheet should be available for you. Yeah, so that way you can kind of work along. Week 1 here, I'll try to like word the problems the way they do on the sheet, so we know we're on the same page. Oh, and just a warning, I'm not very adept this tablet. I don't draw very well to begin with. So problem 1's scenario. We probably all did this as like a kid in a restaurant. I still do it. You stick your finger on the straw, pull the straw out, and the liquid stays in the straw. It sits there floating. And it asks us a few questions about that. First one is kind of an easy one. Maybe it's deceptive at first, though. It says, what's the total force acting on the liquid in the straw? Now, what that's asking is, if you think of the liquid in the straw as an actual object, like a cylinder of water or something, there's forces acting on it. There's forces acting on everything. What can we say about the total force acting on it? It doesn't want to know a number. It doesn't want to know the sources or the names of these forces. It just wants to know, what's the total force acting on it? And here's a quick and dirty answer. It's not moving. So the net force is 0. And actually, that's the correct answer, because the way the question's worded, it wants the quick and dirty answer. It's just saying, what's the sum of all the forces on it? B is the one that wants some explanation. B is, well, let's write up a diagram of all the forces acting on it. So let's do our force diagram from 2A. Why am I immediately drawing an arrow? It's an object with some mass. So it's going to have this force of gravity. I know there's a lot of different notations. Some people just use a capital W for weight. Some people do F for the subscript W. Basically, I'm talking about the force that's mass times gravity, right? The mass of the water is obviously like its density times its volume, blah, blah, blah. We're just talking about its mass, its weight. So if it's not moving and the force is 0, and there's a downward force of mg, that means there has to be, oops, let me try to get that line a little straighter, has to be some upward force. And that upward force has to be the same magnitude, so that when you add them together, they come to 0, because one's pointing up, one's pointing down. That means one's a negative of the other. That force And I'm going to write out, I'm going to give like the spoiler of it first, and then we're going to describe what's going on here. That force is the change in pressure, or the difference in pressure from the outside pressure versus the inside pressure, times the surface area of the water. I'll just put A. You can say pi r squared, you know, but we're not worried. We're not worried about exact quantities. We're just going to say the surface area of the liquid in there. I'm noticing I'm jumping between saying liquid and water. Liquid's the more general term, obviously. That could be any liquid in that straw, and my mind is just jumping to water. I'm sorry. So that's it. That's it for B. That's the diagram. We know there's a weight force point pushing down, and there's a force of a difference in pressure pushing up. C asks, is the pressure inside the straw greater than, less than, or equal to the pressure outside of the straw? So it wants to know if it's less than, equal to, greater than, outside. We'll think of it this way. In reality, if we're not even thinking about the gravity force, there should be two pressure forces. There should be the pressure in times the area. We can't just say pressure because pressure is not a force. Pressure times area is a force, right? The pressure that's up here will be pushing down on this surface, and the pressure that's outside here will be pushing up on this surface of the water. Well, if it adds up so that there's an upward force due to pressure getting rid of the gravitational force, that means the total force due to pressure has to point up. That means pressure outside has to be large enough so that it cancels out pressure inside and still points up. So that means pressure inside is going to be less than the pressure outside. It might not make sense at first, but that's what D is for. Part D is asking, how does that happen? How does the pressure inside get different than the pressure outside? What I gave for part C just now is the explanation that tells you that it has to be less than. In part D, how did it get that way? Well, this is going to be more of like a long drawn out explanation. I can't really give a one word answer here. Here's the idea. The straw's in the water. Oof, man, okay, let's try to draw it. Let's see how this works out. Straw's in the water. All right, you plug the straw up with your finger and pull it out. There's a much sloppier picture now. Plug the straw up with your finger and pull it out. And the first thing that happens, maybe you've seen this happen, maybe you already know the answer. You pull it out and a little drop of water comes out, maybe two, maybe a big drop of water, I don't know, but something falls out initially. So what does that do? Well, let's draw it here. That means while the straw is plugged up, my fingers get sloppier and sloppier the more I draw them. At the instant that it comes out of the water, that's what it looks like. And then when that little drop falls out, it loses some, right? So then the surface has to drop down a bit. If that surface drops down, that means this headspace, this area up here, the volume increases, right? If the circular cross-section of the cylinder stays the same but it gets taller, it's obviously increasing volume. Now, I hope we're familiar with the ideal gas law. I hope that's something he talked about. If not, it's gonna pop up. It's a relationship between the pressure and volume of a gas, its temperature. R is just some constant. It's like pi. It's just a value. It's got units and stuff, but it's not something that can change. It's not something that you need to like solve for or anything. It's got an exact value that doesn't change. And N is the number of molecules in that thing of gas. So temperature is not changing. R is a constant, so by definition, it's not changing. We're not putting in or taking out any gas molecules. So that means this has to stay the same. This whole value over here has to stay the same, but our volume's going up. Well, how do we make this number over here stay exactly the same while we're making one of these numbers go up? Make the other one go down. So when this volume increases over here, that means the pressure inside goes down. Now, before you put your finger on here, the top was open up to the atmosphere. We had pressure, atmosphere here. We had pressure, atmosphere in the straw. Even when you plugged it up, it was still pressure, atmosphere in the straw. It wasn't until this volume increased that that pressure had to go down. And as soon as it goes down to a point where it's low enough that the force from the atmospheric pressure will cancel out the weight of the liquid, then it stops. So that's how that happens. I feel like I went through that a little fast. I'm sorry if it was too fast to catch anything. Is there anything about it that just sort of like comes across as making absolutely no sense? Or maybe I went through something too quickly? Anything that just sort of like brings up a big question? And if you're not comfortable asking questions over Zoom, there's a text chat option. There's an option to email me later. There's, I mean, any and all forms of communication that are available, I will try my best to respond to them. Okay. Again, I'm gonna try to get this video to you. I don't know if I should do like a shared folder, Google Drive or something, or if I should try to get a YouTube channel. I don't know if that's a good influencer platform, doing really bad physics problems, but we'll try, right? So, problem 2, we're dumping cold water in a hot metal container. These are very generic problems, right? Like, does it even say a cup? I don't know. So we have, this is hot metal. This is cold water. I'm not trying to be cool with the H2O, it's just it's easier to fit it when I'm trying to write on a tablet here. Okay. Part A, after we put this cold water in this hot metal, what are some physical measurements we can make to see that there's changes going on in the system? There's a lot of things you can measure. It's a very problematic question. But what it's getting at, because it's physics 2B, we're talking about thermodynamics and energy. The 3 things we can measure temperature, we can measure volume, and we can measure pressure. I guess I should write out temperature since I wrote out the other words, but now you see why I didn't do it, because my handwriting's terrible. Okay, yeah, if there is a change going on in this system, it should be present in a pressure change, a volume change, a temperature change, some combination of them, or maybe all 3. B, what are the conditions for equilibrium at which no changes are taking place? It sort of gives away the answer there, I guess. Basically, here's the flow of logic here. Thermal equilibrium means that there's no heat being exchanged between the 2 bodies. And if there's no heat being exchanged between the 2 bodies, the temperature will be stable. What does that mean? That means whether it's the water or the metal, the temperature won't be changing over time when it's in thermal equilibrium. In most cases, in fact, for this course, I think in all cases, it means they will be the same temperature. If you put very cold water and very hot metal, cold water will heat up, the metal will cool down until they've reached the same temperature. Now, it's not always going to be meeting in the middle, right? In fact, I mean, we know that intuitively just from having done these things like in our lives. You're not going to take like you're not going to take a room temperature coffee mug and put very hot tea in it and then just have them meet somewhere lukewarm in the middle right away, right? The coffee mug is going to get very hot too, and then it's going to come to equilibrium with the room. Other factors go into deciding what temperature they reach, and we'll get into that when we get to them. Right now, the basic idea is that hot things, when in contact with cold things, the hot things will cool down, the cold things will heat up until they reach some meeting point, and that's thermal equilibrium. That's B. C, sort of worded a little strangely, but it's good enough, I guess. C says use the concept of energy to describe how the cold water is interacting with the hot metal. Well, temperature, I'm just going to use capital T instead of writing the whole thing out. And I'm writing an arrow here because it's not exactly equal to, it's just related to. Temperature is related to and sort of is a measurement of the average kinetic energy of heat-carrying particles in the mass. There's a lot of strange sounding words there. I'm just trying to be very precise in what I say. In metal, the metal atoms themselves, like copper or steel, it's not like they're all dancing around and bumping into each other. They're in a lattice. That's a solid. They're staying still. The electrons of those atoms are sort of zip-zapping around all in different areas. Those are free electrons. Now in water, it's the actual water molecules that are bouncing around. So generically, we call them the heat-carrying particles. It's the average kinetic energy of them. So not average speed, because remember, kinetic energy is also involving the mass of the particles. So you can have something with very massive, slow-moving particles and something with very small, fast particles, and they can be at the same temperature. But I'm getting too much into it. So if you look at, let's say we have the water on the left. Here's the interface of the water and the metal. Let's say we're like zooming in to this area or something like that. We have water molecules sort of, you know, slowly meandering around. And then we have the heat carriers, the electrons of the metal, zipping around pretty fast. So over here it's hot, over here it's cold. At this interface, now remember, what's the magic number? 10 to the 23rd. Whenever we're talking about macroscopic things like an actual cup of water or something, we say it's on the order of 10 to the 23rd water molecules in there, on the order of 10 to the 23rd electrons in that metal. 10 to the 23rd just means there's 23 zeros. It's a massive number. So obviously there's way more of these circles than I'm drawing here. So at any given time, very hot electron hits the wall here and is colliding with a very slow water molecule. Think of like a game of pool, right? You have like, I'm gonna try to draw a pool, right? The 9 ball, it's standing still. Your cue ball is going very fast. It hits it, it comes back. It's not there yet. There's the future cue ball, and then this guy goes off this way. What happens? The slower thing leaves the collision going faster than it did. I mean, it wasn't even moving at all. Now it's moving, so it has to be going faster. The thing that was going fast may still be going fast, but it's simply leaving that collision going slower than it was before. And that's what's going on here. These really fast particles over here may still be going fast after the collision, but they'll be going slower than they were to begin with. These things may still be going slow, but they'll be going faster than they were to begin with. And that's happening 10 to the 23rd times at any given time. And it happens over a course of times until these things have given off enough kinetic energy to these that they are going quite slow. These things have taken enough kinetic energy from them that they're going faster than they were before. And again, they won't match their speeds, but they will match their measurement of average kinetic energy. But that's sort of like the microscopic view of what's happening here. These really fast, really energetic particles are crashing into very slow, very not energetic particles. And just like two pool balls or two cars or something, they're giving energy off to each other when they collide. And D asks, is this something we actually observe? Do we actually see what, like I drew here in this picture? No, we don't see that. We're not looking down there and watching them zip around like what's that old game, Jez Ball on Windows. I don't know. Look it up. You'll be amazed at what people used to entertain themselves with. Yeah, no, that's not actually happening. It is actually happening, but it's not actually something we look at. This is sort of like a model. It's a classical mechanical model of what's going on. This is not something we actually see. It is something that is inferred from the macroscopic measurements. Macro meaning big, scope meaning vision or view, just means how you're looking at things. Microscopic is the view of the tiny things. Macroscopic is the view of the large things. And it doesn't always mean optical view, like with your eyes. It just means how you're approaching it, how you're imaging it. That should be it for number 2. I hope most of that makes sense. Really, this whole idea of temperature being related to average kinetic energy is sort of what it's trying to drive home. It wants you to have this model in your head, but it wants you to know that, you know, we don't actually watch that happen. This is just what we're sort of extracting when we do a temperature or pressure or volume measurement. I forgot to write the number 2 there. Hope we all knew it was number 2. Again, these are available on iLearn, usually the night before. I will try to put them on the discussion page iLearn as well. They're available on the main page, as will be the solutions at the end of the week. But again, I'll try to make a way to get these videos out if you find these helpful at all. Okay, number 3. Number 3 is sort of long and drawn out. It's a good interlude to talk about one of the concepts here, thermal energy. Oof, I will try to get better at my handwriting. Okay, thermal energy. You take an object or a system, you see how much heat is flowing into it, and you see how much work is being done on it. And that's the thermal energy. I know it sounds like an oversimplification, but that's really it. The concept's a little more complicated than that. Heat is probably the easier of the 2 things to understand. Heat is just energy going into or out of something that isn't like mechanical energy. Nothing's being pushed, nothing's being smacked with a hammer, nothing's being, you know, pulled. Like we're not like compressing something with a bike pump or like pulling the bike pump open. There's no mechanics going on. There's just energy moving in there somehow. So we call that heat. Work done on. This is the classic trip up point in this class. There's work done on a system or an object and work done by a system or an object. And they're kind of the same, but they're not the same. I'm sorry, but I'll give you more on that. They're the same in that when an object gets work done on it, it's mathematically equivalent to say it did negative that amount of work itself. So if you do 3 joules of work on a nail by smacking it with a hammer, mathematically it's equivalent to saying, well, that nail did 3 joules of work. There was 3 joules of work done, negative 3 joules of work was done by the nail. So in that sense, you can kind of think of them as related. In some situations, it'll be more intuitive than others. But when we're talking about work done on, think of, because work is always mechanical work. It's pushing something, it's smacking something, it's sliding something across the floor. Is the object the one doing the work, or is something else doing that work to it? If something else is doing that work to it, it's work done on. If it itself is doing the work, it's work done by. And I know that makes it sound super easy, but it'll get tricky in some scenarios. But yeah, that's the first way to think about it. So this gives us a list of scenarios and wants us to think about, you know, how does the temperature change? What's the work done on it? What's the heat flowing in? And what's the change in thermal energy? Oof, sorry for that. A little note on notation here. Maybe you see this big triangle in front of something. That's the Greek letter delta. You know, maybe in another class you might have seen this is delta. That's lowercase delta. The triangle's capital delta. And all it means is a change. So if capital T is temperature, delta T means what's the difference in temperature or the change in temperature. You know, so it's usually a comparison from one point to another. If you say delta T, there's usually a T1 and a T2, and we're looking at the difference between them. Capital E is usually always going to mean energy. That little subscript TH just means we're specifically talking about the energy that comes from the thermal properties. We still treat it as energy. It's still joules. Still every concept of energy we know in existence applies to it. You know, there's the conservation of energy and everything. It's just from specific sources. It's not anything different. The first scenario is we take a hammer and we hit a nail. And we're talking about the nail itself. So let's start with the obvious things here, right? Work done on the nail. Well, it's positive. We're hitting it with something. We're doing work on it. Heat going into the nail. Now you might think, okay, well, you know, you hit something, that's friction, something warms up. That friction, that's from this mechanical work we're doing on it. There's no flow of heat in the sense that there's no energy being imparted to the nail that's not coming from some sort of mechanical action, like the swinging of the hammer or the smacking together. There's no just intrinsic energy being given to it from some outside source. That's zero. Now, thermal energy is Q in plus Q on. 0 plus some positive number is going to give us some positive number. And I want to say 70% of the time, that's really just a number in my head. Usually, I'll just use the word usually. Usually, these are related in the sense where, oh, thermal energy went up, temperature goes up. Oh, thermal energy went down, temperature goes down. There is an example, and it is in this problem. There is an example where that's not the case. There's very specific examples, and there'll be a key to figuring out when that happens. All right, the other one is we're holding a nail over a Bunsen burner. Right away, the obvious one. There's heat exchange. Fire exchanges heat. Fire is not doing mechanical work to anything. I know, like, it'll make light things, like, because the air pressure changes, the air will sort of make things float above it. If you ever burnt a tea bag or something like that, that's actually work done by the air itself. But anyway, heat is going to be exchanged when there's fire. Let's just try to get that in our heads. It's not doing any mechanical work. That nail's not moving. Nothing's pushing it. Nothing's smacking it with the hammer. The nail's standing still. But same concept applies here. 0 plus some positive number is going to give us some positive number. And if the thermal energy goes up, the temperature is going up in this case. Okay, we have a bike pump. We're compressing it. That's important. I guess it's not in this case, it's a pump, so we're always going to be the one doing it. When we compress something in a bike pump, we're doing mechanical work on it, right? And this is another case where there's no heat exchange. This is looking identical to the hammer on the nail. So I'm going to do the next two and then sort of speed through the three after that, because I do want to get to number 4. There's some important concepts too, but the next two are important. Here's some vocabulary. This one says we allow we allow some gas to isothermally expand while holding it over fire. Isothermal. Iso is just going to mean something doesn't change. The second half of the word is going to tell you what it is that doesn't change. Now, I mentioned the ideal gas law before. I mentioned this PV equals nRT, and if you're not familiar with it, trust me, within the next week, he's going to cover it in lecture. It should be something that pops up. And now the molecule number can change, but let's not worry about that. And R is a constant. Let's focus on those 3 that we talked about at the beginning of number 2, temperature, pressure, and volume. Thermal. Thermal means we're talking about temperature. So this means in a situation where the temperature doesn't change. That's what isothermal means. The other 2 words you're going to have to worry about are, for pressure, isobaric, and for volume, isochoric. You might go through this whole course without ever seeing the word isochoric, but it might come up. So put it in a note somewhere, or I don't know, if it shows up you know, you're gonna be doing homework at home, Wikipedia it or something, right? But you heard it here first. Isochloric means the volume doesn't change. All right, isothermal expansion with fire. Well, isothermal means temperature doesn't change. It's the definition of it. There's no situation ever where we're going to say isotherm or isothermal and have temperature change. Here's a little more subtle thing. Actually, no, let's go with one of the obvious ones. It's over fire. It's heat exchange. Fire gives us heat. So now, what we got to figure out what we can put for work done on to know thermal energy, right? And I know we can just jump to it and say, well, the temperature doesn't change. It's probably 0. Yeah, and it is 0 here. But in the next case, you'll see why we can't always do that. We can go, yeah, we'll talk about it in the next one. But work done on the gas. When a gas expands, it is doing the work. Now we're giving it the heat to allow it to do that, but we are not the ones making it expand. We are not grabbing the boundaries of the gas and stretching it out and saying, hey, take up this volume now. We're giving it heat and it itself is expanding. So it's doing the work. Work done by would be positive, but work done on is negative in that case. Temperature doesn't change. Thermal energy is not changing. Positive, negative. They're not always going to be exactly the same, but in this case, they are. All the heat that goes into it is going into expanding. That's what this case is. So this last one here that I'm going to go into detail on, I'll just draw the answers for the rest. We're going to boil H2O into steam. Well, again, when you boil water, it's over some sort of heat source, so heat's going into it, right? Now, the work here, there actually is no work. Now we're thinking like, oh, okay, well, if a gas expanding itself, is the gas doing work? Surely, when water turns into steam, it's doing some work to do that. It's not. It's expending energy to do that, for sure. But it's not doing any mechanical work. It's not like when a gas expands, it's pushing against the walls of some container to expand itself. When water goes from, when water goes from the liquid phase to the vapor steam phase, it's a chemical change. It's a chemical thing. There's no physical, there's no mechanical change there. So there's no work done on or by it here. So in this case, well, there's heat going into it. There's no work being done. That means we have to be having an increase in thermal energy. Now you want to jump over here and say, well, that means the temperature's changing, except there's this little caveat here. When something is going to a phase change like this, when we're going from water to steam, or some steam to condense into water, or water's freezing into ice, the temperature doesn't change until everything has switched. When you have ice in water, it's going to stay at freezing temperature until all of the ice melts, and then it can go up in temperature, or until all the water freezes, and then it can go down in temperature. But while they're both coexisting, while there's two phases there, it's going to stay stuck at that phase changing temperature until the entire mass there changes phase. So when we're boiling water into steam, that water is going to be at boiling temperature until all of it's gone, until all of it's turned into steam. Then the steam can start rising in temperature, but when they're coexisting together, the water and the steam together are going to be the same temperature. So that is the case where these aren't going to match up. It's a very specific case. It's the phase change that trips us up on that. The other direction is definitely a more surefire thing. The other direction of saying, hey, temperature changed, thermal energy changed. Yeah, that's a more surefire thing. Thermal energy change means temperature change. That's the one where you gotta look for this caveat. Okay, we got 10 minutes. I want to have enough time to do number 4. So steam turns a turbine We have a crate sliding across the floor, and we have a piston in an engine. I'm going to write the answers for these, and you can always email me any questions you have about them. Might be something to help you sort of think about it too. But yeah. You can sort of see how the steam turning the turbine is kind of the same concept as a gas expanding and pushing a piston, right? That's why they look identical there. And then part B is just asking, do these follow the law of thermodynamics where thermal energy is heat in and work done on? And yeah, they do, because they have to. No, that's not the reason why, but yeah, I mean, if you go through them, they all do. It's kind of a dumb question to ask because we had to assume that they did to solve some of these. So it's really not helpful to put that question at the end. All right, I'm gonna move on to number 4 because there's some important concepts involving engines that we want to talk about. And I want to get at least 2 important examples done on 4 before we run out of time. Here's the main concept of an engine. You are going to have, we call it a heat reservoir. It's just an area of very high temperature. And that temperature, we're going to call it TH. And then you have a cold reservoir, an area of colder temperature that we call TC. And thermodynamics tells us that heat will only flow from a hot body to a cold body. Heat will only flow from a reservoir of high temperature to a reservoir of low temperature. It's never going to go from, without any external work done, it's never going to naturally go from cold to hot. Refrigerators do that, but that's because it doesn't happen naturally. We have to put work into it to do it. So heat will flow from here down, and we stop it. We go, wait a minute, okay, if there's going to be heat flowing in this direction anyway, and heat is energy, I'm just going to put a little machine here, and I'm going to use some of that energy, if you don't mind, to do some work. You can do work by, you can do work out, whatever you want. That's not a ratio, that's saying or. You can say this or that. And it says, okay, that's cool. You can't take it all because you're not the cold body that I'm flowing to. But there we go. That's the basic concept. Heat is going to flow from hot to cold. We're going to snatch some of that with some machine and make it do work. There's limitations on how much of that we can take out, and that'll come into play here, right? Basically, first of all, let's talk about the efficiency. Efficiency in any case, I think maybe there's a lab that goes over this. In any case, efficiency is the ratio of what you want over what you pay to get what you want. In this case, we want work out of the machine. And what is going into the machine to give us that is this QH. It's not QH minus QC. That's just what work out is, right? If we want to conserve energy, then the energy coming out has to equal the energy that went in. What we pay is QH. Well, you can think of QC as like tax, right? Like you paid $12 for something. It was really only worth 10, and you had to give $2, you know, to taxes or something like that. That's an excessive tax rate. That's very unrealistic. But anyway, the point is, that's what you're looking for with the efficiency of an engine. Along came that guy Carnot. He developed the Carnot engine, and it's the most efficient an engine can be. It's a model of a very efficient engine. And what that is it's a ratio between this temperature down here and this temperature up here comes into play, right? The easy way to remember it is that efficiency is a percentage, right? And we go from 0 to 100%, or in this case, 0 to 1. 1 is 100%. So we start off at 100% and we subtract some number from it. And we know it's a ratio between these two temperatures, but which is it? Well, we're not going to go with a negative efficiency. It's going to be a positive number between 0 and 1. So the only way that works is if this next number here that we subtract is between 0 and 1. So it has to have the smaller number on top. If the larger number is on top, then this ratio is larger than 1, and we get a negative number. So this is the maximum efficiency of an engine. And then this is the particular efficiency of that engine. And the idea is, if we don't understand what maximum means, we'll write it out here. The efficiency of the engine is always going to be less than or equal to the maximum efficiency. Simple as that, I guess. If you want a refrigerator, spin all those arrows around. We suck heat out of the cold reservoir by putting work into it, and then we spit that heat out to a hot reservoir. That's why the back of your fridge is so hot. We're sucking heat out of the fridge by using energy that we get from electricity, and we're spitting it out to the heat sink coils on the back of it. And those don't go by efficiency, those go by, I always forget what the P stands for in COP. It's coefficient of something, but it's no longer a percentage. For a fridge, your COP is you want to take a lot of heat out of the cold reservoir, and you have to do it by putting work into the machine. And then the max for that is something very different looking. You have the cold reservoir temperature divided by the difference between those two temperatures. Does that make sense? The way you can think about it is, to make these a number you can add or subtract, 1 is the same as saying TH over TH, right? So the maximum efficiency of a Carnot engine is actually TH minus C over TH. You just flip that over and make this H of C. Maybe that's not helpful, maybe it is. It's good to have multiple ways of looking at these things. I have 3 minutes, actually less than 3 minutes, probably 2.5, to go through 2 examples here. And the 2 I choose are the ones where the numbers are the same and they swap them around. That's to drive home this idea of the maximum efficiency that I just erased. TC over TH. So here's an engine where the heat reservoir is 600 Kelvin. We take 10 joules and put it into this engine. We spit out 4 joules of work and 6 joules of waste to a 300 Kelvin reservoir. The question that we're supposed to answer for each of these is this a viable engine? Is this something that can exist? All right, well, first of all, does it violate conservation of energy? No, it doesn't. 10 joules of heat goes in, 4 plus 6, which equals 10 joules of heat comes out. That's fine. Work out plus QC has to equal 10, has to equal QH. That's the relationship between them. The energy coming out has to equal the energy that went in. But what's the efficiency of it? Well, work out is 4, QH is 10, so you can say it's 40%, you can say it's 4 over 10, you can say it's 2 over 5, however you want. What's the maximum efficiency of this engine? 1 minus TC over TH. TC is 300, TH is 600. 300 over 600 is the same as 3 over 6, which is the same as 1/2. 1 minus 1/2 is 1/2, or 50%. That checks out. It's less than the maximum efficiency. Yeah, that's something that can work. The next example is that we swap these. We say 6 joules is coming out as work and 4 joules is waste. Well, nothing else changed. The maximum efficiency is still 50%, but now the efficiency of the engine is 60%, which exceeds the maximum efficiency, which means that it's not a viable engine. It can't happen. And that's just because of the mechanics and the thermodynamics of heat flowing from the hotter body to the colder body. A certain amount of it is going to have to make its way there. So we can only utilize a certain amount of it for the work that we're going to do in the engine. Yeah, that's it for the time for today. Again, I'm going to have these solutions written up and put on the discussion iLearn. I'm sorry for everything being split between the 2 iLearns, but I only have access to post stuff to the discussion one, and I like to post extra stuff that usually isn't posted on the main one. But yeah, I'll get the solutions on there. I will have my office hours completely spelled out for exact times before tomorrow afternoon. But emails on iLearn should be on both iLearn pages. But you can email me any questions. You can, yeah, you can set up, if office hours fall at a time that you can't meet for them, you can always sort of set up a different time with me. I think I mentioned this already, but yeah, like if that happens a lot, I'll just change my office hours to that time, because usually the way it happens is person who can't make it to office hours is a person who goes to office hours all the time. So I'm just like, well, I should just make office hours at that time then. But anyway, what's the last bit? Oh yeah, office hours are this same Zoom link with the same password and everything. I'm just using it for both discussions, for both office hours. Yeah, and I'll figure out how to do attendance, but everyone's here for week 1, so don't worry about that. And I will see you Monday.
Thank you.
No problem.